In this video, we're going to talk about properties of normal distribution. So unlike discrete random variables, we cannot simply substitute a value into a formula. Recall, with classical probability, we always divide by the total number of possible outcomes. Well, this chapter we will be covering continuous random variables. With a continuous random variable, there are infinite number of possibilities. To resolve this problem, we compute probabilities over an interval of values using probability density functions. So we'll start by discussing uniform and normal distribution. So first off, a probability density function is an equation used to compare probabilities of continuous random variables. It must satisfy two conditions. The total area under the graph of the equation of all possible values of the random variable must equal 1. Just like all the probabilities of a particular event add up to be 1. The height of the graph of the equation must be greater than or equal to 0 for all possible outcomes of the random variable. So again, we'll talk about two in this section, uniform and normal. So let's start with uniform. So suppose someone calls you on your cell phone. We'll let capital X represent the time starting after you click the connect button. You don't like being on the phone, and the longest you'll stay on the line is 60 minutes, and will hang up on the person at any time. Draw a picture to represent this scenario. Remember, with uniform distribution earlier, all of the possibilities were exactly the same. So here's what I'm going to draw. I will draw a rectangle starting at 0, ending in 60, and I'll break it up into intervals of 5. So here's what this picture is going to look like. So the area of a rectangle is length times width. But you know the area's got to be 1 thanks to the first probability density function condition. And the length is just 60 minus 0, that's 60. So the width for this entire problem is going to be 1 over 60. Okay, let's take a look at part B. What is the probability that you will hang up at exactly 10 minutes? Well, here's exactly 10 minutes. Well, that length of a line segment is 0. The width, we've already figured out, is 1 over 60. So the area here is 0. Part C, what is the probability that you will hang up between 5 and 10 minutes inclusive? Well, that's this particular region. So the length, 10 minus 5, that's 5. Width is 1 over 60. That's 5 over 60. That's 1 over 12. Part D, what is a probability that you will hang up after 15 minutes? So it could be any time in this particular interval, starting at 15 and finishing up at 60. So 60 minus 15, that's 45. Width is still 1 over 60. That's 45 over 60. That is 3/4. So the probability of a single value occurring in a continuous random variable is 0. That's where part B came into play because that said exactly 10 minutes. If I said exactly 30 minutes, probability is still 0. At exactly 45 minutes, still 0. The area under the graph of a density function over an interval represents the probability of observing a value of a random variable in that interval. Some continuous random variables are symmetric and bell-shaped. This is what is referred to as the normal curve. Okay? So some random variables that are symmetric and bell-shaped are IQ scores and weight of babies. A normal probability distribution. This is a continuous random variable that has its relative frequency histogram shaped as a normal curve, symmetric and bell-shaped. This is also referred to as the normal distribution. And I have provided some examples of normal probability distributions below. Okay, so properties of the normal density curve. The normal curve is symmetric about the mean. Because the mean is equal to the median, the normal curve has a single peak, and the highest point occurs at the mean. The area under the curve is 1. The area under the curve to the right of the mean is half, and the area under the curve to the left of the mean is a half because it's symmetric. As x increases or decreases without bound, the graph approaches but never touches the horizontal axis. The empirical rule applies here. So how do we interpret the area under the curve? Well, there's two ways that I can do this. One way, the proportion of the population with the particular characteristic that's described in the problem is blank. Or the probability that a randomly selected individual from a population having a particular characteristic that is described is blank. Okay, let's take a look at this example then. So it was reported in 2014 that the mean number of Facebook friends for 18 to 24-year-olds was 649. Assuming the distribution is normal and the standard deviation is 150 friends, answer the following questions. Now, when we talk about distribution normal distribution, symmetric and bell-shaped. So for part A, let's draw the normal curve. So this is what this is going to look like. So we know in the middle is the mean. Well, the mean 649. The standard deviation is 150. So if I go to the mean and go to the right, what am I doing? I'm adding 150. 649 plus 150 is 799. 799 plus 949. 799 plus 150 is 949, so on and so forth. From the left of the mean, 649 minus 150 is 499. 499 minus 150 is 349. Okay, part B. Shade the region that represents the proportion of 18 to 24-year-olds who have more than 799 Facebook friends. This is what this is going to look like. Okay, and in part C, suppose the area under the normal curve for 18 to 24-year-olds who have more than 799 Facebook friends is 1,600. Provide two interpretations for this result. So let me write the two interpretations below. The proportion of 18 to 24-year-olds that have more than 799 Facebook friends is 1,600. Or the probability that a randomly selected 18 to 24-year-old person has more than 799 Facebook friends is 1,600. As a quick side note, the equation or model to use to determine the probability of a continuous random variable is called a probability density function. The normal probability density function is given by the formula below. We will not be using that in this course. That's more of an FYI for you.